Okay, so we just finished this example where we took this second order ordinary differential equation. Okay, we converted it into two first order ordinary differential equations, and then over here on the MATLAB we used Euler's method to go ahead and figure out the profile of v, which is kind of this intermediate sort of step of dy over dx, and then y, which was the actual sort of variable of interest that we cared about. And we used kind of v as an intermediate value, whoops, sorry about that, to calculate the profile of y, or the solution of y at all time. Okay, I tried out a few other things about changing my y initial and v initial. Okay, and I went off and I calculated the exact solution right here. Okay, we don't need to worry about that, but I put the exact solution in black dots. And so what I need to come in here is change that third one to exact, and so that's what's new from this slide. I'm going to hit run. Okay, and if you can see it, then we have these points right here, okay, that are the exact solution, and then we've got our y value right here, and it's starting at -9 as I had before, and v starting at 5. Okay, and so we've got some sort of oscillating behavior that's decaying over time, so now we're going to play around with the t final. I'll set it to be twice as long. Okay, I'll set y initial to be, let's say, 5, and I'll even let v initial start off at 0. All right, so this is kind of the decaying sinusoid that we were talking about or working with, and I need to change that legend, so let me just go do that here real quick. And Control S, pop it over here. All right, so those dots are the exact solution, and of course we're doing a good job with extracting out the profile or the solution, which is going to be a function of an ordinary differential equation. All right, well, let's go back then to our final example for this particular set of lectures. Okay, and we were going to do this example right here where we're going to, first of all, not use ODE45. This is a solver, but we're going to first of all take this equation, we're going to try to convert it into two first order ordinary differential equations. We're going to pop it into what we had before, and then we're going to see the difference between what we have for Euler's method, or Hoynes method if we did RK4. We'll just keep it at Euler's method right now, and then we're going to pop it into ODE45. All right, so the first thing we need to do is we need to convert it, of course, into two first orders. And so we're going to come up here and we'll say that d theta dt is equal to omega. Okay, if dt is omega, or if d theta dt is omega, which could also be known as theta dot, okay, the first derivative of theta, well, then we're going to need another equation down here, which is going to replace it. So we're going to have d omega dt plus b over ml squared, okay, times omega plus g over l sine theta minus m over l squared sine. This is going to be, I'll call it omega r for a value that was added equals 0. Okay, this is going to be some sort of driving function. Okay, and so we're going to play with this w, I'm actually going to call it r later on. All right, well, now that we've got two equations, okay, we need to go off and try to convert these into, well, some sort of Euler's method, okay, to figure out ultimately what this is over all time. So we're really after this, okay, for time equals 0 to time equals, well, I don't know, we'll say 10 again, okay? Okay, and since we have two equations, we need to have two initial conditions. So two initial conditions, okay? So what we need to do is that we need to have initial conditions for theta, okay, at time equals 0. And we'll set that to be, I don't know, maybe we'll say 3. And then we also need theta dot at time equals 0. And maybe we'll say that's starting off at 0. Okay, so this pendulum is starting, okay, maybe somewhere right here. okay, some sort of position, okay, and then it's going to, well, fall down, it's going to swing through and then fall back and forth. So we expect some sort of oscillation to go on with this particular pendulum. And this, of course, is a major topic for system dynamics in a future class you're going to take. But we're going to spend our time not necessarily coming up with this equation right here, but trying to take this equation and numerically, okay, trying to numerically solve. Not analytically, okay, but numerically using, well, in this case, Euler's method or ORD45, how to extract out what omega is over all time, okay, and also what theta is over all time, or what theta dot is for all time. All right, well, let's go off and let's try to type it in. Okay, well, we have a whole bunch of values that we need to plug in, and so we're going to go off and define those first. Okay, and so we're going to set b to be some sort of value, and I'll set it to be equal to 0.5. Okay, and it's going to be kind of an evaluation of the damping. Okay, but in terms of just thinking of it as some sort of coefficient that's going to go in front of this term is probably the best way at this point. Okay, we're going to have gravity, okay, and we're going to have that at 32.2. We'll do imperial units, so feet, per second squared, which means that I need to come over here and I need to define the units for B, which is going to be pounds times second times foot. Okay. We have L, which we'll set to be 0.8 feet. So this is going to be in terms of feet. And then we've got M, okay, so it's the mass, and we're going to set that to be just 1. Okay, and we'll use slugs instead of kilograms to be consistent with the units. And then our WR, okay, our sort of external sort of driving force, or rather torque, I should say, in this particular scenario, will be set at 6. And we'll set this at rads per second right there. Okay, so these are all of our variables, okay, and we're going to come through here and we're going to set this, first of all, taking a look at our equations over here on the right hand side. Okay, we need d theta dt, okay, is going to be a function of, well, what is it going to be a function of? Well, it's going to be a function of everything, like theta and theta dot and some other stuff, and effectively all it is theta dot. Okay, now we got to do the other one. Whoops, I don't want to do that. I want to do a Control C. Okay, the second one is going to be, well, omega, or theta dot. Okay, and it's going to be a function of a whole bunch of things. In this particular case, it's going to be all these other things with the sign in front of them inverted. Okay, so we're going to come in here and we're going to go minus b divided by m divided by L squared times, well, we have an omega right here, okay, which is nothing more than that theta dot. So we're going to times that by theta dot, okay, for this first term. Okay, remember that positive sign is changed to a negative when we bring it over here because we want to isolate this first derivative right here. Then we need to go minus g divided by L times sine. In this particular case, it's not theta dot, okay, or omega, it's going to be just theta. And then we have to do the last one right here, which is again going to be m divided by L squared times sine of this WR thing, okay, times t. Okay, and so we're probably going to get some problems here soon because we don't have a function that is a function of t, so we need to come in here and we need to add t to it. Everything else is going to be constants right here. Okay, well now we need to do our initial conditions. So, well, what do we have here? Well, we had two initial conditions. Okay, we had theta, so theta initial is going to be set at 3. Okay, and then we had theta dot initial, and that was going to be set at 0. Okay, so now we don't need these values right here, or these values. Okay, we do need to talk a little bit about our t, because now it's not a function of x, it's a function with respect to t. So we'll come in here and we'll set t to be some sort of large value. Let's do just 0.1. Okay, we'll go back and set it from t initial to t final. And once we make that, well, we have to go off and define it. So t initial is at 0 seconds. T final is equal to, let's say, we're going to do 10 seconds, I think. Yeah. Okay. And now, right, well, what are we after? Well, we're after theta for all time. Okay, we want to know the angle, okay, of this pendulum for all time. So it's going to be the same length as our time vector. So let's go back and change this into our time vector. Okay, and then we have theta initial right here is going to be, well, theta 1. And then the exact same thing for theta dot. Okay, we don't always care about the angular acceleration, but we use it as an intermediate value, and so we actually get it for free, and so we need to track that as well. So our, let's see, theta dot, not theta dot initial, but theta dot, okay, is going to equal the same length as everything else, okay, and then we need to initialize it, all right, with our, well, theta dot initial right here. Okay. Well, now let's go into our Euler's method and kind of think about how this is going to solve. So we need to go from 1 to the length of theta. Okay, and then we need to change these, and using these equations right here. So we'll come in and we'll do the first one of theta, which means this one has to be theta, and this one has to be theta, and this one has to be not dt, but dx. Okay, and then we need to change what's inside for the arguments of theta dt. It's a function of, well, theta and theta dot. Okay, so it's nothing more than this guy right here. So theta dot I and theta. But of course we can get by just removing this first argument if we wanted to. Alright, that's going to give us what d theta dt is, okay, or d theta dt is, what omega is. Then we need to go off and do the other one. This is going to be our theta dot. So we're going to change our vector right there. We're going to grab theta dot right there and right there. Okay, and then I'm going to copy and paste this over right here. Okay, but of course we need to match the 3 different elements. So theta, theta dot, and now we need to update t. Okay, and I'm going to do ti right there. Okay, and of course our increment, our time step, needs to be dt. Okay, and we come back down here, and now we need to update our figure. So we have t as the independent variable. We have theta, okay, in which we want to track. Then the same sort of thing with theta dot and t. Okay, and all of this, of course, was the other example, so I'm going to just comment that out. Oh, I need to grab a little bit of that legend and make the first one theta, the second one theta dot, and we'll put the location in the same spot in the northeast. Alright, so all we've done then is taken a second order ordinary differential equation and done the exact same thing that we did before, okay, in the previous slides, with a generic sort of equation. We can go back up and look at it here. It was this one right here. Okay. Okay, and of course we're using some imperial units, but we can of course convert this to some other things, and maybe we will a little bit later. But essentially then we've got the same sort of process, and now we've got Euler's method, and of course we can do the same sort of thing by taking the average of 2 different values in Hoyne's method, or taking a weighted sum average as according to the RK4 method that we talked about. We'll just stick with Euler's method, and then we'll go off and we'll try to plot this graph. Okay, so after we run it, here's the results. Okay, and every single time that we look at results, we need to ask ourselves, are we using the right method in terms of if our method that we're implementing is going to have some problems in terms of stability or of consistency. And what we're seeing so far is that there might be some sort of unbounded process of what theta is doing. Okay, so it's always a good place to kind of go and to decrease dt first of all, and see if we get different results, just like we saw beforehand. All right, and now I've decreased dt to 0.01, and so we're starting to see a couple of things. In this particular case, we can see that there are, well, two sinusoids, one is theta, one is theta dot. Okay, and sure enough, it's slowly reaching some sort of steady state, and I don't know, it's kind of hard to tell if it's decaying or not, so let's increase the time from 10 to say 40 seconds. Okay, and it looks like generally it's still up, slowly decreasing down to some sort of steady state that maybe has been reached right now. Okay, well, we've got this y-axis of theta or theta dot, so it might be nice to kind of break these up. Okay, and so at this point then we're going to actually use subplots. All right, so we're going to have theta on one of the subplots and theta dot on the other subplot. So in terms of what we have to do to our figure, we just have to come in here and set a subplot, okay, and we'll have it a 2 by 1, okay, by plot, and we want to access the first one, and so just to kind of show what goes on, I do subplot right here. Okay, subplot, it's going to create axes in tidal positions. Okay, so there's kind of two ways. We're using the first one, m n times b. So the number of m, okay, that's the number of rows, then n, number of columns, and then p is the pth axis for the current plot. Okay, so again, if we want a 2 by 1 sort of plot, we have 2 rows, 1 column, and then we access the first or the top this way and the second this way right here. Okay, so back up here then, we're going to have 2, 1, 1 for our first plot, and then 2, 1, 2, and now we don't need to have a hold on at all, because we're going to put theta in the first one, and then theta dot into the second one right here. Okay, our y label now can be associated with that subplot. Okay, so we're going to do theta on the top. Okay, and then we're going to do theta dot on the bottom. Right? And now this legend isn't necessary, but we're still going to have different colors as it is. And for helping us out, we're also going to try to use a grid. So we'll turn grid on for that first plot, and then grid on for the second plot. Oops, not grid on for the second plot. All right, let's go off and run it again. Okay, and here now we can see we've got two little sinusoids. This is theta. Okay, it's going out to 40 seconds. Maybe we'll decrease that here in a second. And now we've also got theta, which is going from, you know, minus 12 to about 10. Okay, so it's kind of interesting. But overall, it looks like we've got those two sinusoids. So I'm going to change this back to 10. All right, and of course this first one starts off at 3. Okay, theta starts off at 3. That's our initial sort of angle for the pendulum. And the other one starts off at 0. But what happens if we start actually both of them at 0? Okay, so I'm going to come in here and I'll change that to be 0. We'll run again. Can we see then that theta starts off at 0 and it slowly increases and it's wobbling back and forth, and of course this is in radians. Okay, and theta dot starts at 0 as well, and it slowly also increases. And the question now is, if theta dot, this is the angular velocity, is it accelerating so much that it's unbounded? Well, again, let's change it back to, let's say, 40. Okay, and then this is the results that we have. So effectively, we have this pendulum. It's going to swing back and forth, as a lot of pendulums do. Okay, and the reason why it's not dying over time is that we have some sort of external driver. Okay, effectively, we have this little value right here that's driving some sort of torque into it. So let's say we turn that off. Okay, So we're going to make this value be 0 inside sine, and sine of 0 is always 0. And I'll rerun it. And sure enough, we have a pendulum that starts at the equilibrium point, just sitting there, and it stays sitting there because we have no sort of driving torque. But now let's give it a little bit of some angle to start off with. And so it starts off at 3 radians, okay, which is almost pi radians, so almost 180 degrees, okay, and then of course it's going to wobble back and forth, crossing to that equilibrium point, trading kinetic energy for potential energy, okay. It's going to be 90 degrees out of phase with theta dot, or the angular velocity, and of course eventually it's going to reach steady state because we have some damping. Of course, now let's give it a try. Let's try to remove some of the damping, so B becomes 0 now. Okay, and so we have a major problem right here, okay, because effectively we have no sort of reason to stop it, and so we're going to reach some numerical instabilities in this particular simulation. So let's put some damping back on. All right. And then we're going to make this pendulum a lot heavier, so we're going to, instead of 1 slug, we're going to make it 10 slugs. We'll see what happens over the 40 seconds. Okay, and then same sort of thing, we've got some interesting problems because theta is being driven down, okay? So maybe then that we have some problems with our numbers, or numerically we have some instabilities. So let's try to increase our dt, or rather decrease our dt by a little bit more. Okay, and now we're back. Okay, so effectively the lesson is that sometimes you're going to have ODEs where you have values that are constant, and they're actually going to drive if the solution is going to be stable or not, okay, for the Euler's method. Right, now that our dt is small enough, we can maybe go back and check B again. Okay, so let me just pull up a figure. Okay, and now let's make this back to 0. Oh, looks like we still have that same sort of problem where it looks like it's not stable. So we're going to come and change dt even smaller. Okay, and now we get some other weird artifacts. Okay, so it looks like it's somewhat stable for a while, but then it kind of loses its stability. Okay, so we're going to do one last check to see if we can fix this, but we're going to find out that maybe Euler is insufficient. Alright, so now we've got some weird sinusoid happening. It doesn't decay, and that's expected because, well, sure enough, we don't have any sort of damping, and so we'd expect this pendulum to go back and forth forever. Alright, so I bring that up because we need to recognize that based upon the ODE, which is defined by these two equations that are first order and all these coefficients in front of them, you can cause an ODE to be somewhat unstable if you don't use a method that's good enough. So now we're going to go off, we're going to replace Euler's method with a Runge-Kutta method, okay, called ODE 45. Okay, I'm going to change these back to all what we had before. I think this was 6, this was 0.5, and this was only 1 slug. Okay, and we'll start it off at 0, 0. Okay, because now we have like that driving equation right there. All right, and I'll make this somewhat stable right there. Let me just check it to make sure that it's looking good. Okay, so here it is. I'm going to go back down to just 10 seconds. All right, so this is what we're going to try to have for our ordinary differential equation and the initial conditions that we've specified. Okay, well, we've been playing around with Euler's method a lot, and it's got some limitations. Okay, so recognize that we have to go to really small DTs, and of course, since we all know that you can only go so small on a computer, it's better to also explore other methods. And ODE45 is a solver inside of MATLAB, okay, that does something very similar to the Runge-Kutta for method that we just talked about. So let's do help ODE45. Okay, and let's take a look at what it says. And it says it solves non-stiff differential equations, medium order method. So we know a little bit about order method, okay, and then these kind of non-stiff differential equations goes beyond the scope of this class. But in the DiffEq class, you might talk a little bit about these differential equations, and in system dynamics or in ME 335, you'll talk a little bit more about these as well. We are okay knowing that this particular equation and all the equations in the final exam will be non-stiff, and so we can use ODE45 to solve for, well, the important thing is here is the output and the time. Okay, and so we can go back and it'll kind of explain what T out is and Y out. Okay, what this is then is very similar to the Euler's method, but we can fill in these type of things, okay, with what we have. T span, as expected, is nothing more, okay, than T initial to T final. So we can come in here and we can replace T span with this vector right here, okay, T0, T final, or we can come in here and just take T final and T initial, okay, and that's going to be the range of the time. Now, it says right here we have a Y naught. Let's go talk and take a look at Y naught. Well, Y naught is the initial conditions of Y naught. Okay, well, how many initial conditions do we have? Well, since we had a second order ODE, we actually have to have two initial conditions. Okay, the initial conditions are theta initial and theta dot initial. So we're going to need to come in here and make a vector of, sure enough, those two values. Theta initial, okay, and theta dot initial. Okay, well, if we have those two initial conditions, all right, and we have two profiles, well, this Y out is related to those two dimensions, theta and theta dot over all time. Okay, so once we run this one line, we're going to get a time vector, we'll explore that as well, and we're going to get a matrix where each one of the columns in this matrix is going to be related to the different dimensions of our problem, in particular theta and theta dot right here. The last thing we need to talk about is this ODE fun. Okay, and this ODE function needs to be linked to a function that defines, okay, the two outputs, or rather the two slopes that we've solved with anonymous functions up here. Okay, so we're going to come in here, we're going to make a new file, and it's going to be a function, okay, and it's going to return, okay, some sort of generic x dot, yx dot. Well, if you recall, there was two x dots. The first one was going to be d theta dt, and the other one was going to be d theta dot dt. Okay, so both of these, okay, were going to be first derivatives, the first one of theta and the second one of theta dot, or you could even say theta double dot. Okay, so when we take a look at these functions right here, x dot is going to be returned. Okay, so x dot is going to return two values. Okay, this one, or the first derivative of theta, okay, which is this guy right here, and then the first derivative of theta dot, which is, well, d omega dt, or d theta dot dt. Okay. Essentially, then, all we're doing is taking these two equations and we're going to return them in the form of a vector. All right. Well, let's talk about this function right here. Let's call this, you know, equations of motion pendulum. Okay. And what does it take in? Well, it takes in a couple of things. It's going to take in time. Okay. How do I know that? Well, again, I take a look at all the values that are possibly inside this particular function, and so there's theta and theta dot. Okay. And then there's going to be x. Okay, and x is going to be a state vector, or it's going to be a vector that's going to contain all the values that I care about, in particular theta and theta dot. Okay. So inside this function, okay, I'm first of all going to make my output, my return type, x dot equals zeros like we had before, and it's going to be a vector of length x, and number of columns are going to be 1. Okay, this is not a row vector, this is going to be a column vector. All right. Now I need to go off and I need to define input parameters. Okay, and these are related to all these things beforehand, so I'm just going to copy and paste these, okay, into my function right here. B, G, L, M, and this WR value right here. Okay. And then I need to define two variables. First of all, theta, okay, which is x1, meaning that this vector comes in, and I take the first element, and it's going to give me theta. Okay, and I'm also going to take the second one, and that's going to equal theta dot. Okay, now I need to go off and define these last return variables. This first one, as you recall, was going to be d theta dt, and that's nothing more than theta dot. Well, theta dot is actually described right here, so I can actually come in here and just say theta dot, or I could come in here, and I'm going to suppress this one, okay, but I could also just bypass it and call it x2. Why is that? Well, because x2 is the second element in this input vector, and it's related to theta dot, and theta dot is related to x dot, where x, the first element, is going to be theta. So I'm doing nothing more than taking this equation right here, okay, and putting it over into a function that returns a vector of outputs, and the first one is, sure enough, nothing more than d theta dt, which is d omega dt, d theta dt, which is omega, which is theta dot. All right, and now I have the other one right here, okay, so I'm going to go off and just copy it. Okay, and since all these values, b, m, l squared, so on and so forth, are defined, I should be able to use, okay, these values and isolate d omega dt, okay, but I then have to use, well, either x1 or x2 or theta dot. Okay, so theta, right, is defined right here. Theta dot is defined right here. Omega r is defined right here. T then, okay, is going to come in through the inputs. So effectively what I have is I'm making a vector, okay, where the first element inside of the x dot vector is related to this guy right here, and the second element is related to this guy right here, which means it's a first derivative of a vector, and that vector is composed of theta and theta dot, such that I would have right here theta dot and theta double dot, or the angular acceleration, and here the angular velocity. So why is this nice? Well, once I have this vector right here, all I can do is call ODE45 to take these values and add slopes to them. I'm adding a slope to this one, and I'm adding a slope to this one for all the different times in between this t-span, in between this time range. The last thing I need to do is I need to save this, so I'm going to save it as OEM pendulum. Okay, I don't have OEM pendulum, that's good. OEM stands for, actually let me change this to EOM, equations of motion for pendulum, not OEM. I'll make that into EOM. Okay, and now I need to make a connection from this file right here over to my OD fund, or rather to the first argument in OD45. Okay, so let's go down and take a look at it. There's a little example that they have right here. Okay, you can link it this way, or you can also link it with, well, single quotes. So I'm going to link it with single quotes right here. Okay. And we're going to go off and run this, and then we're going to explore what T out looks like and what Y out looks like. Okay. I'm going to run. All right. Some things have been published to my command window. Okay, I still have my equations of motion right here. Okay, so I'm going to go off and first of all explore things, and then I'm going to plot a few more things on this figure right here. Okay, the first thing is I'm going to go to my workspace. I'm going to take a look at T out. Okay, so I'll go double click on T out. Okay, and sure enough, there's 321 doubles. That's interesting. Okay, it goes from 0 to 10. That's good. That's my range. But you'll notice then that the time steps for every single time is a little bit different. It's about 0.01, but it does change over time, which means that OD45 is going to try to take adaptively defined time steps. Okay, we'll play with that here in a second. That's T out. Then I want to take a look at Y out. Well, Y out is actually a 321 by 2 double, which means that there are 2 columns, and there should be the same amount of points, and there are 321. Okay, and we know that the first column is associated with the first variable. So let me slide this over here a little bit. Okay, and we know that the first variable is related to theta, or theta initial. And theta initial starts off at 0, okay, and it ends at some other value, 0.1402. Same thing with theta dot. Okay, it starts off at 0 and it goes to something else. I'm going to actually just come up here and change theta to be 3 again. I'm going to hit run. We're going to take a look at how these things change. Sure enough then, T out, right, is still defined with a single column vector of 321 points. Y out then has these 2 variables. This one, of course, related to theta. It starts off at 3. And this one, of course, is theta dot. And now the initial conditions have changed the values, but eventually they're going negative and positive. Okay, both of these are going negative and positive because we expect some sort of oscillation behavior. Okay, and so now what we're seeing then is that OD45 outputs a time vector. Okay, and we define that time vector in Euler's method. Okay, right here, and all the outputs. And the outputs are going to be linked to what we care about for the initial conditions. We're going to need one initial condition for every order of our particular ODE. So what's left now is to extract these out and then publish them or print them on top of our subplots. Okay, so the first thing we need to do is that we're going to do a subplot after we hold on the first subplot. Okay, and it's going to be Y out. It's going to be T out versus Y out. But it's not just going to be any one, it's going to be the first column. Okay, so the way we call the first column is that we take all the rows with a colon right here, and then the first column, and we're going to make it into dots that are black. Okay, let's run this and we'll see how good we do. Okay, so we've got these black dots right here. And overall, we're pretty close with our Euler method, but it may be that there's a little bit of difference because of the stability, right, of the Euler method like we saw before. Okay, let's do the same sort of thing, but now we'll do it with, let's say, green dots on theta dot. So I'll copy and paste it right here. We now want to use the second column, and then we'll pop this over and make it green dots. Okay, so we're doing a pretty good job. Okay, we're getting really close, but there are some problems and instabilities. Okay, and so now we'll come back and we'll see if we can get these tighter by changing dt for Euler's to see if it gets closer to OD45. All right, with a dt of 0.01, the black dots have not changed at all. Okay, the only thing I did is that I decreased the step size, and now we can see that for both of these, we're doing a lot better. And so even when, for Euler's method, 0.01, okay, there was still error. And so in the previous parts of this lecture, you knew that there was going to be differences between the true or exact answer and the approximate answer, whereas now OD45 is a better method for performing ODE solutions. And so we can kind of compare this solution to, well, our perfect solution in OD45. The good thing about OD45 is that all of this stuff can be done in maybe just 1 or 2 lines. So once you have your functions, okay, I'm going to make one more here. This is going to be OD45 example. But I can take this one line, okay, the equation of motion already defined right here, okay, T initial can be set to be 0, T final can be set to say 10. Okay. And if I know something about my initial conditions where I want to start it off at 3 and 0, all right, all that's left then is outputting. So I can quickly do a figure. I'll do figure 2, just keep different. Okay. And I'll go off and I'll take this code right here. I don't have that fade anymore. I don't need to hold on at all. Okay, and so I've got my initial time, my final time, my initial conditions for the first dimension, my initial conditions for the second dimension. Okay, and then I run this, and I'm going to have to run it, and I'll save it. So short code for ODE 45. Okay, I get these results. All right, I can turn, of course, grid on if I wanted to. All right.